2002. Starting out the multiple section, new topological perspectives on superconductors and quantum magnets. Welcome everybody. The speakers this afternoon, I'm just doing Nick, right? Because then I have another meeting. I'm gonna have to miss one.
That's right. That's fine.
So we're delighted that this starts off with Nick Butch. There's no better way to start this. He started a whole field single-handedly, and I'm sure we'll be talking mostly about that. He has appointments at the NIST Center for Neutron Research, University of Maryland Quantum Materials Center, and the University of Maryland Center for Nanophysics and Advanced Materials Research. He's also the recent winner of the Samuel Wesley Stratton Award for his work on topological superconductivity. So without any further ado, let's just let Nick share a screen and enjoy his great talk.
All right, Laura, thank you. Hopefully this is the correct screen. Okay.
Looks good.
First of all, yeah, thank you, Laura. Thank you, organizers. Yeah, it's a great shame that we can't all be there in person, but we can't control the timing of this pandemic. I think we're probably going to still be rolling with it for a bit before we can just say the hell with it and do whatever we want. Yeah, it's lunchtime here, 9 a.m. on the West Coast, and if anybody's joining in from far away, whatever you are, a different time. I was thinking, I watched our talks yesterday, and I was like, how can I follow a talk on COVID, videos of bacteria swarming, and then consciousness itself? It's a pretty hard act to follow. But I hope to at least make a dent here with some of you. And so I'm aware that many of you have already seen a lot of this material, especially the intro stuff, but I'm going to include it for those who may not have. And so I'm going to be all over the place in terms of, we'll start simple and then we'll work up to some new material. I'd like to acknowledge everybody who, I mean, Laura said single-handedly. No, obviously we have got a lot of people working on this, and actually, if you look at the publications on UT too, I mean, it's people all over the world are working on this, and so there's an awful lot of interest in it. Sheng Ren, I should say, was my postdoc when this was discovered, working on it. He's now at Washington University in St. Louis. All right, so this is what the talk is going to be. Basically, we'll lay out the basic properties in the beginning. I am obligated, I believe, to discuss the superconducting order parameter. And then the title of this talk is the neighborhood. You know, my other talks that didn't have a neighborhood title also discuss the neighborhood because one of the ways that we talk about materials is what do they want to be? What are the incipient neighboring phases? And so I'm going to discuss some of our recently posted neutron scattering work and some of the controversy preceding it. And I will also, I guess I'll finish up with the pressure now. So I'm going by Pierre's original rule. I'm going to try to keep this to 45 minutes. And so the pressure might get cut off at the end. I will also say, with the chair's permission, that if you want to interrupt me, please do. I would rather have a discussion in the middle than wait till the very end. And if I miss you, I'm sorry, I just have a limited number of heads on the side. So, okay. So, all right, so we're just going to start with review of superconductors and why. And so this will lead up and say, like, what's special about UT2? So we know that we've got type 1 and type 2 superconductors. And aside from the differences microscopically, maybe in how they work, what's kind of important here is the relationship between the magnetic field and the temperature scale of the superconductivity. And type 1 superconductors basically doesn't usually take very much of a magnetic field to destroy superconductivity. And type 2 superconductors can be quite robust. So for example, in commercially useful superconductors, the TC might be somewhere on the order of 20 Kelvin, and the upper critical field might be of order 20 as well, 20 Teslas. The superconductors we have, with the exception of the pressure induced ones that really haven't had their upper critical fields measured too much yet, shall we say. are the cuprates. And the cuprates have high transition temperatures and high upper critical fields. And the point of talking about this at all is to try to summarize this behavior on a single plot, where we can see, well, you can kind of collapse all superconductors into several groups. Of course, the cuprates in this plot are high temperature and field scales. Things like the iron superconductors are intermediate, and then the BCS superconductors are somewhere on the low end. And I'll just ask you to remember this as we talk about uranium ditelluride without really getting into the microscopic differences yet. So uranium telluride crystals look like this. The ones that I'm going to be discussing have all been grown by chemical vapor transport. This is the technique that we use to make superconducting crystals. It's possible, of course, to make them not superconducting. And in fact, UT2 has been around for decades, was not known to be a superconductor until several years ago. This is the crystal structure. Actually, this is several unit cells just to sort of show the repetition. It's orthorhombic. It's actually body-centered. It has this motif with, let me see if I can get my pointer. Laser. Okay. This rectangular motif of tellurium layer here, and then a linear or a zigzag chains of uranium tellurium atoms. And in magenta here is the magnetic easy axis. So it's in the A direction. It's along the direction of the chains. So this is 4 angstroms, 6 angstroms, and then 14 this way. Okay. This is essentially a summary slide, a statement to you that uranium telluride should be thought of as a heavy fermion compound. We'll look at the electrical resistivity temperature dependence. The slope is negative along the A and B, let's call them the in-plane directions. And then there's an interesting anomaly on the C-axis that we won't discuss, but I will refer you to this archive paper if you're more interested in it. In the susceptibility, similarly, if you look at the B-axis, it's Curie-like and then eventually rolls over and then becomes Pauli-like at low temperature. I don't have the data here on this slide, but specific heat is also enhanced, and you can plot a comparison of the Sommerfeld coefficient and your susceptibility. Uranium telluride looks somewhere here in comparison to other recognized heavy fermion compounds. All right, what do we know about its electronic structure? From angle resolved photo emission, it's clear that there are 2 sets of very highly dispersive bands. And so to first approximation, this is a 2D-like material. These reasons that if they're not obvious now, will hopefully you'll accept later, these must hybridize with F bands at some point. And so the near Fermi level structure is not well resolved yet from photo emission. In addition, there is what looks like an additional 3-dimensional like pocket sitting at the Z point that is not corroborated by calculations yet. And if we look at optical conductivity, there's a development of a sharp Drude peak below about 40 Kelvin, and this is also consistent with the MFT calculations. So the signs are this is a heavy fermion fluid. So here are your characteristic signatures of superconductivity. The first one's UT2, so there's diamagnetic screening in the magnetic susceptibility. Electrical resistivity goes to 0, and there is a big anomaly in the heat capacity. And we'll talk about heat capacity in a little bit, but this is, of course, from the first paper. All right. Skipping over the details of how we measure the upper critical field, the summary is that the upper critical field in this material is both anisotropic and large in every direction. And by large, one metric is whether the paramagnetic Pauli limit is exceeded, and this is true in all directions. So just by conventional estimates, it should be 3 Teslas. So you might not be impressed with a 6 Tesla upper critical field, but if you look along the B direction, it's not only 35 Tesla, but actually it's not really a true measure of some kind of orbital limit, because it runs right into a metamagnetic transition. That is a step in the magnetization at this field. So superconductivity is killed by a change in the magnetic ground state, or the magnetic normal state, shall we say. And so that might actually extend much higher, and I'll ask you to keep that idea in mind until we finally get to discussing pressure. way down in the talk. All right, so far so good. Here is the 0 temperature effective high field phase diagram for this material. On the vertical axis is magnetic field, and on the horizontal axis is essentially field rotation, so field angle. It's centered on the B axis. So the B axis, even though it's not the magnetic easy axis, is for superconductivity the interesting one. There is a finger, a narrow and about 5-degree window about the B axis where superconductivity does extend to 35 Tesla. If you look at the angle dependence below it, you might argue that it looks sort of more conventional 3D-like, shall we say. So the B-axis is special in this regard, and of course, the B-axis is also the direction along which there is the minimum field for this magnetic transition. And then, of course, on this phase diagram is also the Lazarus phase. That is this high field reentrant superconductor that occurs between 25 and 40-ish degrees. And I'll note that even though we have the upper field limit as about 60, we believe that it could go, that it might go higher as well, because it also seems to be sensitive to orientation. Okay, so here's the temperature dependence of that high field phase. Showing here resistivity and diode oscillator measurements. So in the upper left-hand corner, you can just look at that and say, it looks like an upper critical field curve that's just been shifted up by 40 Tesla. And so that, and actually from this data set, you can extrapolate the upper critical field, however you want to call it, it's kind of awkward, to above 60 Tesla. So, and just again, qualitatively, well, semi-quantitatively, just looking at these numbers, this is a ridiculously high value, and of course, it's challenging our understanding of physics. What can actually stabilize this? It's not like there are no ideas, but this is certainly an area of active research. All right, so back to that comparison plot, and I'm going to keep showing this probably until somebody can actually find something that beats the record here. On this plot, UT2 is essentially a delta function. It's got a very low transition temperature on this scale, but the field scale is high. And so with both the low field limit at 35 and then the higher field Lazarus phase is quite remarkable. And so even if we ignore the topological stuff that I'm going to talk about next, it just, on these merits, it deserves a lot of attention. Okay, so we like talking about topological superconductivity, especially in the context of quantum information science. I was looking for a good graphic and I ran into this t-shirt image. A topological superconductor could be a conductor that's powered by donuts. Pretty successful. So the reason that we might care about UT2 in the context of topological superconductivity is because it looks a bit like the uranium ferromagnetic superconductors. I already mentioned that the superconductivity we know, it should be or must be spin triplet because the Pauli limit is exceeded. So without twisting yourself in a pretzel, that's already hard to explain in terms of spin singlet pairing. But the ferromagnetic superconductors are not only spin triplet pairing, they also tend to be an equal spin pairing state, which generically supports the presence of topologically protected Majorana states, which of course many people are talking about as being useful for fault-tolerant quantum computing. And the question we'll ask is, does UT2 check the right boxes? And so I just suggest that these boxes are listed here. We should see some evidence for chiral surface states, evidence for time reversal symmetry breaking, and evidence for a two-component complex order parameter that comes along or is, let's say, responsible or necessary for this. All right, so as many of you know, scanning tunneling microscopy done in collaboration with Vidya Madhavan's group, Urbana shows evidence for the presence of chiral states on the surface. These are chiral in-gap states. They are dependent on the superconductivity, and they care or depend upon the direction of the face on the surface of which they're measured. So although maybe all the details aren't understood, these are, they fit the definition of chiral. Okay, time reversal symmetry breaking comes to us from optical Kerr rotation experiments done in collaboration with Atomic at Stanford. The symmetry breaking coincides, it's close enough with the TC, as shown here, that we measure by bulk techniques. And of course, there is also evidence in multiple samples of a double or two-component order parameter, because there are two transitions in this specific heat. Now, an outstanding question that we'll come to in a moment is whether this is actually intrinsic or extrinsic, and I won't have an answer for you, but we'll talk about it a little bit. And I anticipate that there will be some questions, but if not, we'll just move on. So, in keeping with all of this, the theorists have been very busy describing order parameters that would be consistent with the data that have been published, not just by us, but of course our friends in France, Japan, and elsewhere. And so the ones that have these complex order parameters with the I term are eligible for time reversal symmetry breaking. Of course, there are also proposals for others. And then what we're showing you here from the paper by Shishidu and co-workers is also a proposal for how the field temperature phase diagram might look and how the order parameters might be dependent upon that. Okay. So I mentioned ferromagnetic superconductivity, but at this point, I want to basically point out that we can't rely on the presence of ferromagnetism to give us this equal spin pairing state, because UT2 is not a ferromagnet. And our squid magnetometry shows us that at least at 1.8 K, which is right above the transition, the superconducting transition, this is very paramagnetic. There's no evidence that there's any kind of ferromagnetism. Other studies that are consistent with this idea, muon spin relaxation, and then a further optical Kerr experiment that give evidence or let's just say where the data, either the temperature dependence here or the gross field dependence here are consistent with the presence or proximity. So either ferromagnetic, invoking either ferromagnetic quantum criticality or highly polarizable paramagnetic state, as one might find near near a ferromagnetic instability. Okay. So this is a picture that's from the first paper. I still think it's a little bit clever, but you know, the question is it right? So what is it invoking here? It's basically saying that there is a series of, in this, maybe not a coincidence, they're all uranium-based materials. UG2 goes for superconducting under pressure, but it's a ferromagnet. And as you move towards the left, this tendency towards magnetic order is being decreased. And the tendency towards superconductivity, just, you know, in terms of its critical temperature, is going up. So is it true then that UT2, like these others, is dependent on ferromagnetic correlations for its superconductivity? Yeah, foreshadowing a little bit. We're going to talk about neutron scattering next, which basically within the last year has changed the discussion about this. So from Peng-Cheng Dai's group and then from France, we've got evidence that the dynamic magnetic susceptibility is actually more antiferromagnetic-like. So it's showing peaks or strong scattering, same thing, at non-zero momentum transfers or Q vectors, however you want to talk about it. And when they are looked for near, so signatures of ferromagnetism are looked for near Bragg peaks, as we have seen in other ferromagnetic heavy fermion compounds, or even in the ferromagnetic superconductors, there is no real evidence that there are strong ferromagnetic fluctuations. So, question, why? Yes, Piers.
Yeah, I know there's basically two uranium atoms that are quite close to one another inside the unit cell. Are they coupled ferromagnetically or are they coupled antiferromagnetically?
So Yeah. My answer is ferromagnetically. And let me just back up and say, I don't have direct evidence for that. This, I believe, comes from calculations and then perhaps interpretations of some data, but I don't think that there's any direct proof of that statement. This is an expectation.
Can't the neutron data be analyzed to look at the relative orientation of the form factors? So to look at the relative orientation of the spins on those two sites?
In principle, yes. And so if they form a doublet, and and the magnetization density is different from that of an atomic, let's say F electron, then it would show up in the form factor. I don't know how easily resolvable that would be.
I see. Okay, thanks.
Yeah, I mean that could be calculated, right?
No, well, extracted, I think, from the data, it could be extracted.
But you can also calculate it based on just models of the F electron wave function extent, and then compare it to the data. I will say that from what we see, I think it's going to be hard to say because you would want to have you would like to have a uniform scattering intensity and then have that modulated. And what we see right now is actually very heavily modulated. So the structure factor, the dynamic susceptibility, is already kind of going to more strongly modulate the intensity than the form factor. So I think it'll be a correction. Now I could be wrong. I'm speaking off the cuff here. Principle, it can be detected. For sure.
Yeah, but it would be hard to calculate because you'd have to combine regular exchange with super exchange. It would be a delicate balance to do. I mean, you could do it, and it would be a theoretical prediction. But I think one really needs to know what the experiment says.
Okay, well, I'll go over our data and let you look to see where you think you might be able to determine it. There are some constraints that I'm happy to talk about.
Thank you. Thank you, Nick.
Just in terms of the experiments. Yeah. All right, so the question is, or one question is, well, especially this Nick Butch guy kept talking about ferromagnetic criticality. And, what can lead to these kinds of excitations, and what are the dominant interactions? So you can think about it, of course, as just in a generic case. Is it local? You think about these as local moments, or is this coming from the conduction electrons? So is it RKKY? Is it some kind of a nesting scenario? Or as was proposed by French Japanese group, is this more of an indicative of spin ladder type interactions? And we'll just leave that hanging for a little bit. Perhaps more eyebrow raising is the more recent reports that there is a new resonance, or that is basically, let's say, a change in the scattering that's seen between the superconducting state and the normal state. And not only is it sitting at 1 millivolt, which is high energy compared to the superconducting gap scale, but it's at the same antiferromagnetic momentum transfers as the other strong signatures. And so an initial statement or initial questions were about, well, now that you have this antiferromagnetic or seeming antiferromagnetic susceptibility that's really strong, does this mean you have to throw away the entire concept of spin-triplet pairing? And to our rescue come already several theoretical papers saying, hey, it's okay. Antiferromagnetic susceptibility can still be consistent with spin-triplet pairing. And I imagine that this is actually going to be a quite fruitful line of inquiry in the near future, because it can pertain to things like UPT3 and other superconductors. So it's already kind of opening the door to further discussion. Okay, and so with that in mind, I want to talk about new data from NIST. Many of you are aware that the reactor has been shut down for a while, so this comes from before then. It actually took a lot of effort to grow large enough crystals, especially in the beginning, since we didn't have a lot, factory going here. Actually, we still don't. they're all grown by chemical vapor transport. That's a fairly size limited process. And in order to make a mosaic of 1.2 grams of crystals, it took months to do. And, you know, we were trying to get away with what we could in terms of intensity or mass, but it turned out that we really needed this much. Of course, you can get away with less, but shown by others, but this is a good mosaic. And this work was done on the cold spectrometer max. Okay. So, oh yeah, and cold neutrons, of course, are lower energy. So we're focusing on energies below about 10 millivolts, okay? So this is essentially a map slide, an overview slide of the results. So first of all, on the left, I want to acquaint everybody again with the crystal structure and the Brillouin zone of this material. So it's body center, okay? And that maybe wouldn't seem like something that's going to jump out of the page at you. But what's important here is when we're looking in the HK0 plane, that is the AB plane, and one traverses just in a line along, let's say, a high symmetry direction like B, you're actually leaving the first Brillouin zone. You go into the next Brillouin zone, not into the bulk of it, but actually into the face of it, because the body-centered structure has the shortest vector is actually on the diagonal, okay? And so when one looks at these things in 3 dimensions, the nearest neighbor is below or above. And so when you go just in plane, you're hitting the face of the neighbor. And so actually that Z point that I've got here, this is not, of course, zone center. It's the middle of the face. And you don't see Bragg peaks there, for example. So the rules for where the structural Bragg peaks are they always have to be where the blue dots are. So I have this motif with these rectangles and octahedra just tessellated here over constant energy, or if you prefer, energy integrated. So slices in energy scans, and this is the momentum dependence in the HK0 plane. So maybe the first thing to point out is you see these big bright yellow stripes. They are, they live along the Brillouin zone edges. They coincide with them. And it's interesting that they're only found in the ones that are constrained to being near 0. So in this first Brillouin zone this way, okay? We don't see any scattering. So symmetrically, this line is equivalent to this line. This line is equivalent to this line. We don't detect scattering there. So one supposition is that this might have to do with spin polarization. But actually that would give you something, if all else being equal, that would look more gradual. So here I would say, if you're just looking, you would expect to see this line coming out. Maybe there would be a jog here, dog leg, but we don't see that. So I think it has more to do with the asymmetry of the underlying interactions. There are also some differences at lower energy, in the 1 to 2 millivolt range, that I cannot explain. But again, if I compare these things, which are symmetrically equivalent, there's more intensity in the middle on this guy, and then there are more at the edges here. And some of that is lost. This is a mosaic, of course, so it's a bit blurred. We've got some rotational disorder. But so, okay. So this is not new. This was seen before by both by Pengxing Dai's group and by the French. But we can say definitively that in the HK0 plane, we could really limit it here at these energies in particular. Now, what I want to do is take a look at the energy momentum dispersion, okay, of these excitations. And so in our data set, this is pretty clear because we have the energy and momentum resolution to talk about it. So what I've got here on the left is a map, just borrowed it from the previous slide. And I've got a green vector that shows one trajectory along the k direction, and this magenta one that's just perpendicular to it. Okay, so let's look at the green one on the top, and you'll notice that there are excitations here about 0.6, 1.4, and even here 2.6. Now, Piers was asking about form factor, right? And so even if I were to ignore the dimer, or possible dimerization, magnetic dimerization, let's say, first thing I'd want to do is just look to see if this is consistent with the 5F form factor, atomic 5F form factor. And it's hard to do here least in our data set, because I'd want to integrate, well, I could either take an equivalent slice or I'd want to integrate over everything just to make it more consistent. And at this instrument, we're cutting off the higher energy part on the low Q excitations and the low energy part on the high Q excitations. So I think we'd need to use a different instrument to do this. Otherwise, I wouldn't feel very confident with the statistics that we have about any. Okay. Now, turning towards the Q dependence, I've broken up this part into little steps. You just can see the K values. And here is just the, basically the intensity as a function of energy. You'll see that it's very Lorentzian. So that's nice. And then we can just do fits to this to look at where the peak value. Oh, I'm sorry, I should also say, these are remarkably broad compared to the peak value. So, you know, it peaks at about 4 MeV or a little bit below. And then you're looking at a full width half max. That is, you know, 2 or 3. Or in some cases, it gets very broader than that. So these are not particularly sharp excitations in energy. But you can write it, you can find the dispersion. So here is green. And so what I've got showing here is the dashed line is the zone boundary. And you can see that there's an asymmetry in the dispersion. And it follows the paramagnetic structure in the sense that this is the zone face and this is inside of the second or whatever. I don't know how to count the Brillouin zone here. So that asymmetry is to be expected. Okay? But why I point this out is this is not symmetric about here. That means that this is not probably an incipient new symmetry breaking or long range ordered state. In particular, 4 MeV is actually very high energy compared to this. So this isn't like a paramagnon or something like that. Now, in the opposite direction, the dispersion is flat or flat enough. So it's very momentum independent now. Okay, so far so good. All right, now if we look at the temperature dependence of the intensity, I have plotted here just to heavily bias you the bulk susceptibility along the b-axis, which has this sort of stereotypical, I would call it a heavy fermion behavior. It's Curie-like here, rolls over, and then it's Pauli here. Okay, let's look here. Superconducting state in 5 Kelvin are here, very strong. 20 Kelvin, it's already weakening, but the same structure. And then by 60 K, you can't discern it above background. And that's actually what's summarized here in plot E. Now, again, this is an energy scale of 4 millivolts. This is consistent with 40K. This is consistent with STM. This is the hybridization energy scale. Okay? And these are inelastic. These are excitations. There's a gap. They don't extend to 0. All right. Well, my favorite compound, uranium, ruthenium-2, silicon-2, doesn't go away. In fact, since I'll show you in the next slide why, what jumped out at me immediately. But I want to just do a comparison for you here. Oftentimes I talk about this as being like a, archetype or stereotypical heavy fermion compound, UT2. But uranium, ruthenium-2, silicon-2 was here before, and it has some pretty remarkable similarities, starting with the fact that both are body-centered. That's not really going to tell you something about the physics until I talk about the neutron scattering. But uranium, ruthenium-2, silicon-2 is tetragonal, and uranium ditelluride is orthorhombic. But if you look at the resistivity, you have the same type of behavior, same temperature scales, and the susceptibility, the same thing, if you ignore the parts that diverge for UT2. There's a hybridization gap, same energy scale. And then if you look at the neutron scattering, it's remarkable that in uranium, ruthenium-2, silicon-2, basically its strongest neutron scattering signature is zone edge excitations. Now, here's why it's important. That's tetragonal. They follow the square zone boundaries here. So A and B are equivalent, okay? And then in UT2, you only have these stripes here. Now, you can say, hey, Jane, Nick, that's cool. One of the things that I want to emphasize here is that this uranium, ruthenium-2, silicon-2 is not the only material that's been looked at in terms of neutron scattering in looking at the effects of hybridization of the normalized band structure. But it is, of course, the one that's probably the most studied. There are others. We just don't have a lot of data to compare to. And of course, they're uranium compounds, so maybe they have more in common. But I think there's a real important point. And of course, I was involved in all these studies. So you can take it however you want. I don't know if this is luck or not, but uranium, ruthenium-2, silicon-2 happens to be very tunable chemically. So of course, parent compound is a real pain. It's been with us for decades. We're still trying to figure out what this hidden order state is definitively. But if you put a little bit of iron in, the material becomes an antiferromagnet. And if you put a little bit of rhenium in, the material becomes a ferromagnet. And these changes in the magnetic ground state are very well documented. Now, what's the big deal? These zone edge excitations don't go away. They don't care about the ground state, the magnetic ground state. And I can couch this in different ways. I mean, I can say this, oh, well, just think about it. The hybridization energy scale is bigger than the magnetic ordering scale. Okay, I expect them to be there. But my point is that this is not necessarily a surprise. So these types of zone edge excitations are signatures of the hybridization. They are not related directly to whatever kind of long range order might develop, even in the case of hidden order. Okay, so keep that in mind. That's the takeaway. That means that in UTE2, we don't need to, or we should not assume that seeing inelastic excitations at a finite momentum transfer has anything to do with proximity to an antiferromagnetic phase or not proximity to a ferromagnetic phase. We just can't say. Stop for questions if anybody has anything to say about that. All right. Okay, so we also have data in the superconducting state. And I would say maybe not surprisingly, again, I just told you hybridization is a high energy scale, superconductivity is a small one. The dispersion doesn't change very much. There are some subtle differences in the slopes and in some intensities. And they may be related to the detection or, to this resonance that's been detected by other groups. We can't say anything directly about that from our data set based on the energy resolution that we have and our background and whatever. So that's it for the neutron scattering. Okay, so I've got actually plenty of time here. You'll forgive me. We're going to talk about one of the outstanding issues in this material. And it's been complicated, in the last, let's say, quarter of a year. So how many superconducting transitions do we have? So first thing we want to do is look at data under pressure. And that's because not only does the superconducting transition go to higher temperatures as a function of pressure, above about 0.3 GPa or 3 kilobar, but it's clear evidence from AC calorimetry that there are actually two superconducting phases. Now, what's going on at low pressure is an outstanding question, or has been of a recent controversy. But we know that there are at least two superconducting phases, and in fact, perhaps more if one is looking at the field dependence. And when I say more, I mean just the things that are kind of contiguous with these superconducting phases. So, especially from data of Aoki et al., it looks like there can be multiple transitions as a function of field, all in this kind of low temperature, low field. But what's important, or an important question that's relevant to like all the physics here is, how does the presence of two acknowledged superconducting phases under pressure, how does that extrapolate back to ambient pressure? Do you expect that there should be two at ambient pressure? Is there only one? And the second one discontinuously evolves? And this is a contentious issue right now. We know that there, of course, has been sample dependence since the beginning, because the first samples of UT2 did not superconduct until the discovery of superconductivity, and it's possible to make them either way. And there are many publications now reporting only a single transition, regardless of what TC is. And of course, there are also reports of you can cut the samples into pieces, etc. Now, I would say that at UMD, when I made this slide in particular, we always grow samples with two transitions. And this is an important factor because our first publication only talked about one. Until we went back, we revisited it and saw that actually it could be resolved with finer temperature steps into two transitions. So We know that other groups can make it because Los Alamos can make 2 transition samples as well. And of course, actually the French and Japanese have now done this too. So what determines the stability of having 1 or 2 transitions? And I guess I'm also going to ask right now, why aren't there samples with 3 or 4? All right. So on the left, we've got the work from Los Alamos. And I am just highlighting here where their interpretation of their data changed from an extrapolation of having 2 phases at ambient pressure to having none. And that was as a result of improved samples and improved measurements that they made. It's possible, as they reported, to cut their samples into different pieces, and then they measure different contributions to the specific heat. In their case, at least as far as what they've published, they show that there's just a variation in the weight. And I don't have it here, but I believe that the French show that they have cut a piece off of their sample where there's only 1 transition. So the interpretation of this is that there are that the superconductivity is inhomogeneous. The normal states of these varying TC superconductors are identical and cannot be distinguished. Structurally and chemically, they are indistinguishable. That doesn't mean that one can't make samples with different stoichiometries and not say anything chemically or about them, but one can make samples that are nominally identical that have different TCs and sometimes have distributions of superconductivity in them. This is an outstanding issue. The sensitivity of superconductivity to we don't know what yet. So it doesn't mean you don't know that you can't make it dirty. You can. But when you make something that's nominally the same, it's possible that you can't tell the difference. Okay. Now, another issue that's relevant to the physics is what happens to the so-called residual part, low temperature heat capacity, when TC goes up. And it looks like it decreases, but I have not yet to date seen anything that actually shows it going to 0. So it's possible that there's still something there. What is it? As I've said in previous talks, we don't actually know. Okay, it looks like it's not fermionic because the thermal conductivity, even in our first samples, it looks like it should extrapolate to 0. So there's no itinerant carrier. Something exotic here. Okay, so that's the current state as I understand it. Maybe others have a different understanding. All right. So I'd like
Quick question about the last slide.
Yes.
In the plot on the right hand side, which shows quite a small C over T, is there a subtraction going on there?
I don't believe so.
I see. So in those samples, they've actually managed to see. I see. That's the first one I've seen without a really large C over T at low temperatures.
But it's still like well, I mean, C over T in a normal state is about 100, maybe bigger than that.
Mm-hmm.
Originally reporting values of about 50. Okay. And that, of course, what's not shown here is that there's also an upturn in C over T at lower temperatures. I'm not sure what it looks like in this sample. Mm-hmm. And pretty much all publications where C over T is measured to lower temperatures, there is always an upturn.
Mm-hmm. Thank you.
Yeah, and so originally, for example, when we were talking about this, there was a bit of a, let's say it was an issue was raised that there is an entropy conservation, right? It becomes easier when the residual part gets smaller, but one could always in the past have subtracted, I won't call it arbitrary, but a carefully selected entropy to give you entropy balance in the superconductor from the superconducting transition. It was just hard to justify arbitrarily. So people are still looking into what is going on at lower temperatures and whether it's intrinsic or not. Okay.
Sorry, can you exclude? Can I ask a question?
Please.
Can you exclude the distribution of TC, or do you really need to put different TCs?
Well, I mean, if you look at this data set here,
yeah.
Looks like there are two fairly separated transitions. I think I mean, okay. as I said, we don't understand the relationship to the underlying structure or chemistry. Why would it do something like this? I would expect that if disorder were playing a role, that
Yeah.
there's probably a more continuous distribution, right?
Yeah, this is my question, in fact.
Yeah, yeah. Wouldn't it just look like a broadening? And sometimes that's seen, but what's remarkable is that in many / most of the samples, one just gets this bifurcation, yeah? And one never sees 3 or 4,
Yeah.
but 1 or 2, okay? So if we just say this is some kind of a materials issue, why does it behave this way?
Yeah.
And I will also note that even though there may be a relationship with the residual resistivity ratio, and we can say things about scattering, it's not that, it's not a one-to-one correspondence. You know, in some superconductors, you say, this is really dirty. It's got no transition. Okay, this is kind of dirty. It's a broad, ugly transition with a low TC. And here's my magical, awesome sample. And it's got a high TC, sharp transition, and it's obviously the best. That's not true.
You say that there are cases where there is no superconductivity at all?
Yes, yes. So you can make this material that without superconductivity. It generally tends to have a much worse residual resistivity ratio, but otherwise the normal state looks the same. So yeah, so it is possible to tune, but we actually, I'll just say, it's still open research right now. What is actually going on here as it's now several years in. Okay. So pressure. I already showed you the pressure phase diagrams. This is just flashing at you the, based on resistivity, the pressure phase diagram that we published a while ago. So superconductivity is enhanced and it eventually gets killed at somewhere in the neighborhood of 1.5 GPa, long range magnetic order sets. And I want to focus on this data set, not because it tells you something different from the other ones that I flashed at you earlier, but because we have evidence, or we found evidence before, of small pockets of reentrant superconductivity. And if you look, for example, on the right side here, the field temperature scale is very low. So there's a magnetic order, and then at lower temperatures, the system transitions into a superconducting state. And then there's this gray region, it's kind of a mixed phase, okay? So even from resistivity, this is an incomplete transition until here. Now one can ask, do you know that this is actually a bulk superconductor, even with a zero resistance state? And we don't know because we didn't do AC calorimetry here, but this is all resistivity data. So there are pockets of this reentrant superconductivity, reminiscent, shall we say, of the very high field part, in the sense that it lives on the other side of a magnetic phase transition, and it's in proximity to magnetic phase. So here I've got it labeled FM. If one makes fewer assumptions, this is just some kind of long range order. And there are arguments about why it is more consistent in terms of its phase boundary shapes, et cetera, with antiferromagnetism. Okay. Now, we have also studied perhaps the more interesting high field phase diagram under pressure. So that's what I'm going to talk about in the last couple of minutes. So a question is, first, what happens to this really super interesting B-axis superconductivity to apply pressure? So just as a reminder here, on the left is the zero resistance state, and then this jump that's associated with killing the superconductivity. One can track this as a function of pressure, 4 kilobar, 0.4 GPa, etc. And you see that the sharp transition persists, but it is getting reduced in the field value. Okay, so qualitatively, some similar things. There's also signatures of changes in reentrance or whatever that could also be due potentially to some misalignment. But if we want to take these data and make a phase diagram, this is what it would look like. And so this FP phase is above the metamagnetic transition, as I showed you on the other slides. This is getting suppressed to lower field values with pressure. That means that that phase boundary is getting shifted down. Perhaps not something that would blow your mind or shatter your preconceptions. That seems reasonable. Furthermore, when we look at the PDO data, so the diode oscillator data, there are anomalies at lower fields that we've interpreted as phase transitions between two different superconducting states. These get lost above 8 kilobar. Okay, so there you go. Superconductivity. So this phase boundary is pushed down, and superconductivity is limited by it. Same story I told you with the ambient pressure data. And here is just the summary of phase diagram pressure and temperature. I'm sorry, pressure and field at 0.4 K, so effectively 0 temperature with field parallel to B. This phase boundary is pushed down to, again, this 1.5 GPa critical pressure, above which there's signs of long range order. And then there's the second anomaly that looks like a second phase transition. But what do I want to tell you? Pressure decreases this. This is always an upper bound. And when I say upper bound, I showed you before, it looked like the superconductivity is just kind of cut off by the magnetic phase transition. If one does, let's say, interestingly motivated extrapolations, because these extend really high, the initial slope of HC2 extends really, really high, and it's cut off by this just horizontal line in temperature when the magnetic transition when the system goes through a magnetic transition. So if you want, let me plant in your head this idea that this low temperature superconductivity, it really wants to extend to much higher fields. It's actually limited by an underlying instability of the normal state. So if you want to go back to that diagram I showed before, it's even more, it's a delta function with a higher amplitude. It might even exceed this Lazarus phase, or it might be comparable. All right, so and then the final part here, this so-called Lazarus high field reentrant phase and what it does under pressure. So for this experiment, we turn the magnetic field along the BC direction to this intermediate direction. And this is sort of just kind of like a fold out poster board kind of a view of here. So this is what happens along the B direction with pressure. And then of course, we expect that this line is going to be suppressed, but I want to know what happens to the pink part, or this magenta part. I'll also mention, we're talking about how COVID is terrible and how it's ruined all our plans to come together. This data set was collected right before COVID shut everything down. So we were remarkably lucky to get it done. So here's a summary. Many phase diagrams. On the top are tunnel diode oscillator measurements. So again, this sort of contactless conductivity, and on the bottom resistance. At the same pressure, they don't give you exactly the same thing. That is because there is some slight rotation of the sample, but qualitatively, you're seeing a similar thing happening. There is this magnetic phase boundary that is being suppressed by pressure. And then there is your superconducting phase below and superconducting phase above in this case, right? Because this is along a direction where this Lazarus phase is. And if you look at this carefully, in both cases, it's a little bit harder to see in resistivity, maybe because there's some not bulk superconductivity below this line. But this part, just like in the ambient pressure data, this part is limited on the low field side by the magnetic transition. Whereas when you go to higher pressure, it can make a dome, but then the low field part is limited on the high field side, right? So this line is basically, I don't know, you can almost think about it as like a squeegee. It's coming down the screen and then it exposes this superconductivity while it's killing this part. So it's playing this role where it's limiting the superconductivity on both the high field and the low field sides. And then when it goes away completely, that is once we're in the magnetic state, we see additional anomalies that we've labeled A for anomaly, which I will talk about next. So, but before I do that, I wanted to just emphasize here. So this is a data set and several of the pressures where we have a zero resistance state up to 45 Tesla. And it's not very frequently that one sees something like this. So it's kind of cool. Caveat, we think that there's a phase transition in there between two different superconducting phases, but that's very interesting. The other thing that I would just mention here is that, remember in the first pressure paper I talked about there being actually I didn't talk about it, I'm sorry. There's hysteresis that we see there. So these first order phase transitions, discontinuous ones, are hysteretic in field. It's also seen here when one looks closely at this. And of course we have the reentrant superconductivity. So these all seem to be features of this material. And then this A phase, or I won't call it a phase, this anomalous behavior. When one looks at the diode oscillator measurements, which are measuring changes in frequency that are proportional to like penetration depth or some surface conductivity, and looks at the temperature dependence of these things. When you're in the superconducting state, you'll see that, so this is fully superconducting, you see this temperature dependence. And then below it, there is a feature that shows a similar temperature dependence, but we don't see comparable drop in resistance as one does here, where we're saying it's superconducting. Plotted as 1/h for a reason. That looks like it, you know, if one has puts on some rose-colored glasses or something, that this could be periodic and inverse field. And the only reason, really, from you know, an outside perspective to talk about it this way is that Landau levels, as have been shown in, say, in other interesting systems, are a potential avenue to basically killing the orbital limit of superconductivity and stabilizing high field superconductivity. If I were to take this seriously, I would have to explain why this periodicity has this value, because it doesn't correspond to anything we know about the electronic structure, but I'm just throwing it out there. So it's a bit compelling. We don't really know what this is. So let's compare these two phase diagrams side by side, just to take away something. Again, as we expect under pressure, it doesn't matter. In the low field limit, we know that there's a magnetic transition. It seems to be associated with the fact that this high field metamagnetic transition is pushed down to zero field. So there's this line, it should be evident in any field direction you do. In this case, we've got high field superconductivity that's always limited by that metamagnetic transition. On this side, where HC2 is lower, it actually increases, but when it meets this line, it dies. And then the high field stuff, this Lazarus phase, is always limited on this side. And in fact, actually, it extends to higher pressures than we measured here. So, but it looks like it's going to go away eventually. Okay, I mentioned this business about the relationship between the critical pressure and the metamagnetic transition. This is totally consistent with magnetometry done by the Japanese, where they show, for example, at ambient pressure, the B-axis magnetization takes over, is bigger than the A-axis magnetization at this metamagnetic transition. Similarly, as a function of pressure, the B and A axes switch. So A is the easy axis at low pressure, and then the B axis becomes more polarizable at higher pressure. So, all right, conclusions. I at least made a case that superconductivity is chiral and breaks time reversal. We can talk about this a little bit more, but in my conclusion slide. I forgot to mention the ramifications, of course, of having a single transition that would be inconsistent potentially with having a time reversal symmetry broken state. Neutron scattering, I'm going to argue that the things that everybody sees are really signatures of hybridization. They are effects of the normalized band structure, and that this is not a far out idea, that it's got precedent in other materials. And then in pressure, there is an entire crazy neighborhood of superconducting and magnetic phases that have, let's say, a complex relationship with each other. But one easy take-home message from that is that this metamagnetic or magnetic transition is suppressed by pressure, and it separates two otherwise different normal states that actually both support superconductivity. So thank you for attention, and looking forward to more questions.
Thank you, Nick. That was helpful. I think it's probably worth going a couple minutes into the coffee break, because I wasn't going to stop you because it was too interesting. So we've had a few questions during the talk. Do we have any more questions from the general studio audience?
Zilka has a question, I see.
I have one if you like.
Okay, shall I go?
Yeah.
Okay, thank you. So I have a question. So a question on quantum criticality, because your nice blue yellow phase diagram suggests that it could be quantum critical, but from your neutron scattering results, you don't see evidence. Is that correct?
Yes.
Nick?
Oh, well, so my question would be, and I mean, it's not fair to phrase it this way, but what would we expect? So if we want to say something like a quantum critical system should have strong fluctuations, some strong magnetic fluctuations. Now I'm claiming it's ferromagnetic, so we should see some kind of extra magnetic fluctuations, probably around the Bragg peaks, and people have looked for them and they don't see it. Why not? Is it that it's not quantum critical? Is it that we're looking at the wrong energies and the wrong momenta? Is it that the fluctuations themselves are not really that strong?
No, but you have the max data. They pretty much map the Q space, right? I mean, they are
Yeah,
ideal to see quantum criticality, and you don't see really the energy going to infinitely small energies, right? You always have a finite energy where you see intensity. So I would expect that you fill up the energy range, right? And you don't see that.
So I want to be, sorry, I don't call it pedantic, but let me be very careful here. I want to say that everything that I showed you, everything that I've interpreted, has nothing to do with quantum criticality, has everything to do with a heavy fermion electronic structure.
Okay.
It should not be interpreted in terms of quantum criticality. That does not exclude the possibility that there would be an additional component that could be due to critical fluctuations. But you are correct. That is not seen. And if it were to be seen, I agree that it should fulfill the criteria that you stated.
Okay, thank you so much, Nick.
Okay, next, Nick Kuro has a question, which I want to hear about comparing night shift specific heat.
Yeah, so is there a, I mean, this is really intriguing, the statement you had about the zone edge excitations are the signature of the hybridization. I'm just wondering, is there a sort of a simple model or picture to understand why this is?
Oh, there is. In fact, I didn't show it here. I will refer you, actually, we can talk about this later, but I refer you to my paper on the uranium lithium-2 silicon-2. I didn't come up with this idea. Was it Brandau? I think it was at Los Alamos, has a model of, it's like a 2D Anderson lattice. And so generically, one can take, let's say, a D band and an F band, hybridize them, get an indirect gap that spans the Brillouin zone. And then you expect to see the strongest scattering at the zone edge in neutron scattering. And then, you know, if you just take that calculation literally, then it'll have a certain temperature and momentum and energy dependence. So that's the simple model, I would argue. So there is definitely precedent for this. And one can then ask, well, you know, what about the actual electronic structure and your favorite material? Will it make it complicated? That's, I think, the next step in terms of the interpretation. But yeah, just in terms of a simple model, I think there's plenty of motivation. It's actually pretty old.
Okay, thanks.
Okay, Piers, quick question.
Yes, Lazarus phase. You really need two things to make it come about. One is that you want to avoid orbital limiting of HC2, right? And that's your reason for going for a phase in which presumably the field is parallel to the layers of superconductivity. That would be the only way of doing that. But in this system, there's another requirement, which is you're basically using F electrons to make the superconductor, which means you need some kind of Kondo effect going on, which means that you can't have a very large G factor there in those directions. So my question to you is there any evidence for G factors being small in the particular direction in which you have the field in the Lazarus phase?
None that I know of, but let me ask you something since we're talking about it. Okay, let's look at this phase diagram. Let's look at this pressure. Okay,
yeah.
This is Lazarus phase.
Yes.
It's dome shaped, right? It's actually centered at some.
Oh, dome shaped in field. Yes.
Yeah. I mean, the question is what's responsible for the onset, and then actually what's responsible for its death? Like, why?
That is really interesting. Oh wow! Is this published? These curves?
The second thing is your statement about there being an important Kondo effect. I am not sure. Let me just throw this out for consideration. That this metamagnetic transition may actually be associated with the breaking of the hybridization. We know that actually a change in the magnetic state. It has some. It's reflected also in changes in the effective mass as determined by certain quantities. So The thing that is compelling about it, or I think the most compelling argument, is that it seems to in some way connect to the hybridization temperature. So it forms sort of a pocket. It's not a phase transition, but it may be suppressed. It may be that we're breaking the Kondo effect, or maybe not completely if we've got orbital selective blah blah blah. But you know, you're doing something potentially to the Kondo state, maybe changing things. But I don't know then also. I didn't answer your question.
Okay, thank you. This is a very interesting phase diagram. Thanks for bringing it up again.
Ready?
Yeah.
Do you have a quick question? We're past time.
Okay, I have a simple question. Is there any comparison of the non-magnetic, non-superconducting samples with the high pressure cases in which you have suppressed superconductivity? However, is there any work on high pressure on the non-superconducting samples?
It's a great question. There is nothing published that I'm aware of. But yes, that's a very interesting question.
Yeah, because one can wonder whether those correspond to a situation which would be high pressure.
Yeah, interesting.
Certainly.
Okay. Great talk, great discussion. I have questions, but I'm rather close this. I'll talk to you later, Nicholas. So thank you all, and let's all thank Nick again for a great talk.